Hi, Derek of VERITASIUM made a video where he steps into my territory, electronics, and poses a question at the beginning and gives an answer at the end, and his answer is wrong. You should watch Derek's video for full context. Of course, his video is great and highly educational, but his question rubbed me in ways that I didn't like. It wasn't just a physics question, it was a trick question. See, if you want to raise your IQ, you get an audiobook and a great deal from my link in the description thanks to my sponsor Audible. More at the end. But a trick question is designed to trick, not to test your knowledge. Something like, a baby is hungry and will die now if not fed, and the mother is nowhere to be seen. What do we do? I don't know. We strap on a fake breast and feed the baby? No, dummy. Open the closet door. The mom is in there. Hi. The hell? Derek's question was,
imagine you have a giant circuit consisting of a battery, a switch, a light bulb, and two wires which are each 300,000 kilometers long. That is the distance light travels in 1 second.
Well, more like this. Now the question is, when we flip the switch, does it take half a second, 1 second, 2 seconds, 1/c seconds, or none of the above for the lamp to turn on? C is the speed of light, and 1/c comes from the 1 meter distance between the wires over c meters per second, and so the value of 1/c would be the value of time per second. We also make some assumptions.
Like the wires have to have no resistance, and the light bulb has to turn on immediately when current passes through it.
So I jump right to it. Wires with no resistance is possible. We make it out of superconductive material, put it in the shadow of a giant umbrella or earth, keep it super cold and superconducting. The light must turn on immediately as soon as there is current. His lamp is a regular one that can be incandescent or LED and draws a certain level of current when it's on. It takes some time from when there is operating current into the lamp to when it's on. But let's assume it's a special lamp and it will be fully on as soon as there is operating current. And of course, it won't turn on if there is not enough current through it. For operating currents, the electric waves would have to travel the entire length of the loop at the speed of light. So it could take at least 1 second or more depending on the...
After I close the switch, the light bulb will turn on in roughly 1/c seconds.
What? And my IQ was shattered. That was when I understood when he said...
And the light bulb has to turn on immediately when current passes through it.
He meant the light turns on at any current level immediately. You little Derek. It was a trick question, wasn't it? So that's what the mystery black box is for. Something that turns on the lamp immediately at any current level. Well, actually, with that assumption, Derek's answer is wrong. The correct answer is E, none of the above. The light never turns off no matter the state of the switch. When the switch is off, over time, the voltage across it will be the same as the battery voltage, which means there are electric fields across the switch contacts which pull on electrons. Some electrons will jump the gap and result in an extremely small continuous leakage current. Derek never said there is no leakage current, and it is a real thing. The light turns on at any current, so it's always on. And I win! Not gonna lie, Derek's answer triggered me just a bit, so I was thinking about it for over a week every day and night. Which is good, because it brought back a lot of lost memories. Thanks, Derek. Let's dive into Derek's video because I don't quite agree with every point he makes. Here he says, in school we have been taught something wrong, that in an AC circuit the flow of electrons is like a chain moving back and forth, delivering energy to the load.
If it's the electrons that are carrying the energy from the power station to your device, then when those same electrons flow back to the power station, why are they not also carrying energy back from your house to the power station?
Well, I'm sawing wood, pushing and pulling. Both acts of me putting energy into the saw, cutting the wood. Saw is a vessel to transfer energy like electrons in a wire. Just because I pull doesn't mean that I'm gaining energy.
These are the lies you were taught about electricity.
Come on, lies?
That electrons themselves have potential energy.
I think this is debatable and depends on your frame of reference. Hopefully the rest of my video clarifies better.
That they are pushed or pulled through a continuous conducting loop.
Well, in a closed circuit with no capacitive or inductive breaks, they are running in a closed loop.
And that they dissipate their energy in the device.
They do help dissipate the source's energy into the load. Those analogies can make sense, so I don't think calling them lies is accurate.
My claim in this video is that all of that is false.
I think Derek is highly exaggerating, which is appealing to the general audience, but I think professionals expect a bit more accuracy. Then he talks about the true flow of energy from the source to the load. That segment is highly inspired by a video from Science Asylum I had seen a couple of years back, which Derek also credited to. Another great YouTube channel you should subscribe to. In that segment, he talks about the pointing vector. Not pointing, pointing. The scientist who came up with it. In an electrical circuit, the pointing vector shown as S indicates the flow of power with a unit of watt per square meters and is equal to a constant times the cross multiplication of electric and magnetic field vectors. So using the right-hand rule, if the direction of fingers match the E vector and they curve towards the B vector, thumb shows the direction of power flow or energy per second. So Derek shows that in a closed loop of a circuit where we have electric fields between the wires and magnetic fields around the wires, according to the pointing vector, the electrical energy in fact flows in the space around the wires by the electromagnetic fields from the source to the load, which is true. But what's shown here is again exaggerated. It shows all vectors of energy at the same strength. We know that in a straight wire, the magnetic field strength is reversely proportional to its distance from the wire. So a field 10 centimeters away is 100 times weaker than a field 1 millimeter away from the wire. Yes, maybe the electric fields are kind of uniform between the wires, but the magnetic fields are much stronger closer to the wires. So especially for DC, the energy flow looks more like this, with energy much more concentrated close to the wires and at much smaller levels further from the wires. AC is a different beast though. As the frequency rises, the energy will find and radiate through many different parasitic, capacitive and inductive pathways to the load or to the environment. Let me show you how crazy the world of AC is. Here I have a loop of wire connected nowhere, just an LED at the end of it and a 5 megahertz signal coming out of the scope. And if I connect the signal only to the LED, either on this side or the other side, it turns on with no grounds connected.
This also shows it's the fields and not the electrons that carry the energy.
Again, the frame of reference is important. A counter-argument is already in Derek's video.
The current inside the wires creates a magnetic field outside the wires.
So if flow of electrons creates magnetic fields, then why do we say
inside the wires, electrons just oscillate back and forth, but they do not carry the energy?
Yes, fields carry the energy, but
the current inside the wires creates a magnetic field outside the wires.
So to conclude that,
but what we've learned in this video is it's not really what's happening in the wires that matters.
Directly contradicts with
the current inside the wires creates a magnetic field outside the wires.
Electric fields are an inherent property of electrons, or protons for that matter, creating electric fields around the wires. Motion of these charges creates magnetic fields around the wires, and then the fields carry the energy. So to say,
it's the fields and not the electrons that carry the energy.
Sounds inaccurate. Okay, enough of the side quest. Let's focus on the main question of long wires. I'm going to provide some detailed information that is guaranteed to blow your minds. So save your minds now if you have to, and just watch my sponsor segment at the end. But if I see a drop in my viewership, you're just a bunch of traitors. I checked the analysis Dr. Olsen and Dr. Abbott provided to Derek in his video. I also did a ton of simulations and analysis myself, and I was happy to see that my results match theirs. I also double-checked a few things with Dave from EEV blog to make sure I'm not completely on crack. Thank you, Dave, for the videos on the subject. Subscribe to his channel too. But I'm not going to say things the same as other people now, am I? Let's go super basic and replace these super long wires with their equivalent impedances. We don't know what they are and we don't care. As long as there is no significant other way for different parts of the circuit to exchange energy, If current goes in here, same current must come out of here almost immediately, limited by the speed of light. So Derek is right that as soon as we close the switch, we have current through the lamp in 1 meter over c seconds, because the wires are only 1 meter apart, no matter how long the wires are in the loop. But how much current? It depends on these components now. Let's dive deeper. The circuit is symmetrical on both sides, and whatever happens on one side happens on the other side in the opposite direction. So let's just focus on one side. The switch has been off long enough that negativity has spread all over the wires. Only a tad bit of positive charge is here, and as we close the switch, suddenly a burst of positivity travels in the wire at the speed of light. After the burst of current travels 1 meter at the speed of light, the new electric fields finally reach the opposite wire and start pulling on the electrons up here, which means right then we have current flowing into the lamp. What is charges pulling charges between two surfaces? It's a capacitor. Current running through the wire creating magnetic fields and so self-inductance? It's an inductor. This is how we engineers deal with fields around the circuits and lump them into more digestible components. So this long length of wire can be modeled by many stages of inductors and capacitors, each for a defined length of wire. And as the wave travels into this network, it encounters more and more of these stages. The inductance blocking the current and capacitance sucking the charges is why the burst of current flattens out as it travels through the line. For the moment, let's look at the pointing energy vectors. Shortly after we throw the switch and the waves of fields appear in the wire at the speed of light, they still don't know what we have at the end of the wire. All they see is a uniform network of impedances. If we draw the energy vectors around the loop wires, we see that all of them are pointing into the loop and nothing comes out, as if this is a giant resistor sucking all the energy in. Only after half a second traveling through the length of wire, these waves hit the short circuit at the end, some of them reflect and travel for another half a second to add up to the energy going into the lamp. So the waves can travel and reflect multiple times, and these lines being half a light second long, it can take 1 second to multiple seconds before the light receives the full power of the source. At which point the entire length of wire is at the same potential level, so no electric fields connecting them, only electric fields connecting the positive side to negative side. A line like this is called a transmission line, and if we ignore the wire resistances and the leakage between the wires and the line goes to infinity, then the impedance of this circuit is in fact a resistor, equal to the square root of 2 of these L's divided by a C. But if this truly goes to infinity, then the impedance seen from this point forward is no different from the impedance at the beginning. So we can delete the rest of the line and replace it with a single resistor equal to the line impedance. A transmitter would see the same line as if the energy only goes in with no reflections, which means a receiver would be absorbing the entire energy. Now, if the transmitter also has the same impedance matched with the line, we would have the maximum energy transfer between the transmitter and receiver. But that's another story. So back to our Derek lines. Right when we close the switch and the waves haven't reflected from the back yet, this line looks like a resistor at the input. So as soon as the switch closes and the waves propagate at the speed of light, the voltage of the lamp jumps to its known level sharp with no overshoots or further delays. This is not the full battery voltage though, because of these resistors, and the only way to get rid of these resistors is to make the length of connecting wires 0. So if you have any length of wire, initially it is seen as a resistor until the waves reflect from the end and bring the information back that we were tricked, it's a short circuit. Let me show you a simulation.
This simulation does not accurately represent circuit dimensions or effects of light speed, but correctly demonstrates the LC propagation delays in the circuit. Don't watch if you have diarrhea.
Here, I tried to model 40 kilometers of wire round trip or 20 kilometers of transmission line. I roughly calculated inductors and capacitors based on 1 kilometer segments of the line, assuming my wires are 1 centimeter thick, 1 meter apart. Supply is 10 volts and lamp is 100 ohms, so like a 1 watt lamp. Reasonable. Running the simulation, this is the voltage across the lamp. You see, when I turn on the battery, the voltage rises slowly and takes maybe over 15 milliseconds to settle close to the battery voltage. And this is just a 20-kilometer transmission line. And that's not the whole story. If I zoom in, you see the voltage is actually rising in steps. This is the first step, very flat, around 65 millivolts, indicating that the line is acting like a resistor. Here the supply turns on and the waves travel all the way and hit the short circuit here and return all the way carrying the information, and we enter the next step. So any length of transmission line is a momentary resistor at high speeds. That's not the entire story. If I zoom in right at the beginning, you see initially I have a spike of voltage close to the battery voltage because my supply rises at 1 nanosecond. And then it slowly ramps up into the first step. Both the spike and the ramp into the step are inaccuracies due to my model. I put the line capacitance first, that acts like a short circuit at high speed that creates the voltage spike and then discharges. Then the inductance causes the ramp into the first step. This doesn't affect the overall result though. But the truth is the inductors and capacitors exist on the line at the same time. The simulation would be much more accurate but almost impossible if we made our segments much smaller. Maybe every 1 micrometer instead of 1 kilometers, until the circuit would approach a true resistance property. All these oscillations are also due to inaccurate model. Anyway, if I change the inductance and capacitance values so that the line impedance matches half the lamp impedance, or both lines together match the lamp resistance, and simulate, you see the lamp voltage would jump right away to half the supply voltage. There would be no ringing. And after the wave would complete a round trip over the line, the voltage would jump to the full supply voltage. This is the best case for Derek's question. The lamp voltage would jump right away to a decent voltage at the speed of light, and after a 1 second round trip over 300 kilometers, it would jump to the full voltage. But with more reasonably picked values for our case, where nothing matches properly, it will take multiple steps for the lamp voltage to settle, and each one of these steps is 1 second. So where would you pick your voltage and current threshold to turn the lamp on? Low after 1 second? High after 10 seconds? Or to achieve your 1/c second time, you just say any current turns your lamp on. And forget to address the existence of leakage current that would keep the lamp on forever. So was Derek's answer wrong? Yes, on a minor technicality, and because he tried to trick me into giving the wrong answer. But his question raises a great insight into electromagnetic waves. I guess if you also watch my video as a compliment. What would happen if lines were giant circles? Well, you should visit my sponsor Audible. No more excuses like, I have to cut all this wood and I have no time to read books. You'll use my link audible.com/electroboom, or in US text electroboom to 500. And this season, for a limited time, you'll get 60% off first 3 months. That's only $5.95 a month. And you start to listen to any audio title from the largest selection of audiobooks, hands-free. So you get to cut all the wood you need and expand your mind. Ow! I was browsing titles on Audible and saw Green Lights by Matthew McConaughey, and I was like, what does he have to say? I listened to the sample and I was like, dang, he narrates so well. And the story is pulling me in. We should listen to this together. It's perfect for commuting at the gym or just cozying up by the fire. Cozying up by fire, you'll fall asleep right away. I say keep active and feed those brain cells and be super productive by listening to your favorite audiobook title. And the best part? You also get full access to Audible's streaming library, the Plus catalog, where you can unlimited stream tons of podcasts and original content from top creators around your favorite subjects. Things you don't hear anywhere else. With your membership, you can also choose one audiobook title every month, yours to keep forever. So use my link and start being the cyber bookworm you always wanted to be. And thanks for watching.